Hi, so we're looking at section 2.2 in this video, which is organizing quantitative data that popular displays. So in this section and the next section, we're going to look at how we can organize quantitative data. And this section is saying the popular displays. So we're going to look at like what are the most common ways to display quantitative data, and then we'll look at some additional um, ways in the next section. So if you forget, some of these terms I have here to review, you can check those out in section 1.1, pages 7 through 9, or watch the section 1.1 lecture video just to refresh yourself on what's a quantitative variable, what's discrete, what's continuous, right? So remember, a diagram I like to draw with discrete is like stairs, right? So you have to go up to the next stair. So like one, two, three, four, five, and so forth. There's no room in the middle. Where continuous is like a ramp, right? Where I can stop at any point on the ramp, right? So that's something that helps me keep my head around the difference between discrete and continuous variables, right? So in objective 1, we want to organize discrete data in tables. So I have here just a few sentences that says, in summarizing quantitative data, first determine whether the data are discrete or continuous. If the data are discrete with relatively few different values of the variable, then the categories of data called classes will be the observations, just like we did with qualitative data. But if the data is discrete but has many different values of the variable, or if the data are continuous, then categories of data classes must be created using intervals and numbers, right? Um, so it's just saying, we basically, if you have a discrete variable, you don't always you're not always going to do a interval for the classes, right? For like each bar, like each grouping, um, but if there's a lot of different values, that's going to make sense to do that, right? So let's look at an example. So example 1 says the professor of an honor statistics class surveyed the number of siblings of each student. Construct a frequency and relative frequency distribution of the data, right? So we have the data here, and it's also in this file on Canvas. And we want to create a frequency and relative frequency distribution, right? So I'm going to first do this by hand, and then I'll show you how you can do this on StatCrunch. So I'm just going to put this all in one table. So we have number of siblings, make a column for tally, make a column for frequency, and I'll make one for relative frequency. All right, so if we look here, looks like my biggest value is 7, my smallest value is 0, right? So we're going to have 0, 1, all the way to 7. Right, so we're going to do this just like before. I'm going to look through the data and make a tally mark every time I find the number, right? So first number, we have 5, so I put a tally mark here, cross that out, and then I have 1, and then 3, so forth. So I'm going to pause the video and go ahead and do that, and then you can unpause it and I'll have the results. Alright, so here's the results of going through the data and doing the tally marks. And I filled in the frequency, so you should have found that there's 1 0, 4 1s, 8 2s, 3 3s, 2 4s, 1 5, 0 6s, and 1 7. Right? So if we add these frequencies together, we should get 20. Right, so there's a total of 20 20 data points, right? And you can also count the numbers here, right, in the data. So then to find the relative frequency, right? Remember we take the frequency divided by the total count. So I would take 1 divided by 20, 4 divided by 20, 8 divided by 20. Right. So 1 divided by 20 is 0.05. Oops. 4 divided by 20 is 0.2. 8 divided by 20 is 0.4. And then we would take 3 divided by 20, which is 0.15. And then 2 divided by 20, we get 0.1. And then 1 divided by 20 is 0.05 still. And this would be 0 divided by 20, which would just be 0, right? And then 1 divided by 20, which is 0.05. Right? So that is a frequency and relative frequency distribution of that data. And again, typically if you were going to report this, it's okay if you have it in one table, but we normally wouldn't have this. So we would just remove that. It just looks kind of messy, but it's okay for this. But if you were publishing something, you wouldn't want that. All right. So now I want to do this in StatCrunch. So I already input this data in StatCrunch that we're going to use in this video. Both of these data sets are on Canvas under the datasets module. So the file that we're working with right now is titled siblings.csv, which is this variable. And then the state and rate, we're going to look at that later on. So if I want to make a frequency distribution, I'm going to go to stat, then go to tables, and then frequency. And then the variable I'm after is siblings. And I'm going to go ahead and leave frequency and relative frequency checked. Hit compute. And here's our table, right? So you can see this matches up with what we had in the notes. Right, and just notice one thing though, the number 6 is missing. So you don't have to list that in our table. I was just listing 0 through 7, but it would be okay if you left that off as well, right? Since it didn't have any values in there. Alright, so now what I would like to do, which is objective 2, is to create a histogram of discrete data. So a histogram is a special type of bar graph. The difference is with the histogram, the bars are going to be touching each other. Also on the x-axis, that's going to be a quantitative variable, not like categories like we saw in the last section. So it doesn't make sense to have what we call a Pareto chart like we did in last section for quantitative data, because with quantitative data there's going to be values on the x-axis and we can't just switch the order of those, right? Those are inherently in an order, where in section 2.1 we dealt with qualitative data. Like if we have days of the week, it's okay to move those around. It doesn't hurt anything. So you can change categories around, but it doesn't make sense to change like numbers around, right, that are on a number line. So a histogram is really popular, and it helps us see the distribution of the data. So a histogram is constructed by drawing rectangles for each class of data. The height of each rectangle is the frequency or relative frequency of the class. The width of each rectangle is the same, and the rectangles touch each other. Right? So those are all characteristics. So we want to construct a frequency and a relative frequency histogram of number siblings from the statistics class data set, right? So the same thing we had from example 1, right? So we're going to make 2 graphs. So I'm just drawing in like a first quadrant, right, for these. So I'm going to title this, we could do histogram of siblings and honors statistics. Right, so I'll just give the same title here. Right, so then along the x-axis we could label that the number of siblings and if you want to be more specific, you can say number of siblings for the honors statistics students. Right. So then, this is a number line, right? So I'm going to put tick marks 1, 2, 3, 4, 5, 6. Oops, need a little bit more room. 7, 8. Right. So then over here I'll draw frequency. So we need to go up to at least 8. Right. So then when we draw these bars in, something to note is, even though this is discrete data, like we're looking at 0 siblings, really what we're considering is 0 to 1, right? And this is interval notation, so if I draw a bracket next to the number, it means you do include it, and if you draw a parenthesis, it means that you don't include it, right? So in other words, any number that's 0 all the way up to 1 but not including 1 would be in this part, right? But the idea is, this is discrete data, so we can't have anything else, right? So when you draw this bar, to represent 0, it's going to cover 0 to 1, right? So I'll draw this bar in green. So this first bar would go like this. So that's 0 students, or 0 siblings, right? And there's 1 person with that data set. And then, with number of sibling being 1, you would cover like 1 to 2, right? So the next bar would go from 1 to 2 and go up to 4. And then from 2 to 3, we'd go up to 8. And then 3 to 4 would be 3. 4 to 5 would be 2. So I'm just graphing this from that table. And then 5 to 6 would be 1. And then 6 to 7 would be 0. And then 7 to 8 is 1. Right? So that's a histogram of this data. So you can see how it's distributed, right? So I have a lot of students that have two siblings, right? So then if we do the same thing but for relative frequency, right? So the only difference is I'm going to write relative frequency off to the side, and then instead of like 1 and so forth, I'm gonna go up by 8%. So we'll do 0.05. We still need 1, 2, and so forth down here. Right? And then now I'm ready to draw in the bars. So if we're looking up at we're looking at this column now, right? For 0, that was at 0.05, right? So I just need to plot that, right? So 0, 0.05, and then one sibling was 0.2. And then 2 siblings was 40%, 0.4. And then 3 siblings, 0.15. And then 4 siblings, 0.1. 5 siblings, 0.05. 6 siblings, 0. And then 7 siblings, 0.05. Right? So that's how you make a frequency and relative frequency histogram. Right, and just don't forget when you're reading this, right? Like if I'm looking at this bar here, since this is discrete, you're focusing on the left value, right? So this bar includes this left value, but doesn't include this right value, right? And discrete, we only have integers in this case, so it'd be 2, right? So when you look at this bar, this would correspond with having 2 siblings. All right, so now what we're ready to look at is objective 3, organizing continuous data in tables. So I have here, how do you choose the lower class limit of the first class, and then also how you determine the class width, right? So what I mean by the lower class limit of the first class, right, you have, your frequency distribution, right? And this time we don't have discrete, we have continuous data. So you might have, like 1 to 3 here, right? And then, you'd have your tallies, and you'd count how many things were in there and so forth, and then write the frequency, relative frequency, right? So these are known as classes, right? So these classes are like the groupings. The lower limit is this kind of like first number that you're starting with. And then the class width, in this case would be this distance, which would be 2, right? So we want to think about how to maybe how we can calculate those, right? So a common technique is that when you determine the lower class limit of the first class, you're just going to use your minimum of the data. Right? That's one option, one method. And then determining the class width, there is an equation where you take the max minus the min, divide by the number of classes that you want, and then you take the ceiling of that, right? Remember, ceiling is you always round up, right? We looked at ceiling and the floor functions before, right? So like if I have the ceiling of 2.1, this would be equal to 3, right? You always go up to the next integer, right? So if I had the floor of 2.8, the ceiling of 2.8, that would still be 3, right? If I had the ceiling of 4, that would be 4, right? And so forth. So you're just always going to go up, and if you're already at an integer, you just stay there. Right? And so these aren't the only ways, but this is one way to be more methodical, so we're all getting the same frequency distributions and histograms. Right, so here's just some notes about this. So this is more general. So guidelines for determining the lower class limit for the first class and the class width. So something that you want to note is that there's no correct or wrong frequency distribution. There's no wrong histogram, right? But depending on how we pick these lower class limits and the class width, it's going to impact the overall shapes, what we're going to find. So when you choose a lower class limit, right, in general what you want to do is pick an observation that's lower than the minimum, the smallest, right? So for example, it says in table 12, right, in the text, the smallest observation is 65. So that's the minimum, right? So the minimum is the smallest value in the data, and the max is the biggest, right? So they're saying maybe a convenient first class is 50 or 60, right? So that's fine. So on the first page, if we followed those guidelines, what that would do is enable us to get the same the same frequency distribution, the same histogram. So if I gave you specific directions like that and told you how many classes, we should get the same value, right? But here it's suggesting that we can really pick anything as long as it's just smaller than that minimum, or it could be equal to the minimum, would work as well. And then to find the class width, we still have that same equation, but they're saying to round up to a convenient number, right? Not necessarily the next integer. So you can see here's an example here. So if we take the max minus the min, divide by the number of classes that we want, we get 23.419. So if you follow my equation, right, we would take the ceiling of that, which would give me 24. But they're going to use 25. It's just a little easier number to work with, right? So multiples of 5 are convenient. Right, so then here's just some formal definitions of some things we've been talking about, like classes or categories into which data are grouped, right? So there's like these bins or the groupings that we have. When a data consists of a large number of discrete data values, or when a data consists of continuous data, we could create classes by using intervals, right? So that's what we have shown in the last example, right? Or wait, we haven't gotten there yet. So, well, I'd written it out, right? So, an interval is where you're covering multiple numbers, like 0 to 3 is an example of an interval, right? And we often use interval notation here. So if I use 0, 3, right, with a bracket here and a parenthesis here, this is include 0. This is does not include. So there's another way of writing like x less than or equal to 0, less than 3, right? If you're using like inequalities. So we'll use that type of notation. So this is called interval notation. So if you need to review that, you can look up interval notation to review that. So then it says see table 1 below, specifically the age section, right? So that's this section here. So we have this table for educational attainment of the population age 25 and older by age, sex, race, and Hispanic origin and other selected characteristics. And it says numbers are in thousands, so each number is in thousands. So we want to pay attention to that to talk about the intervals. So it says here the lower class limit is the smallest value within the class, while the upper class limit of a class is the largest value within the class. The lower class limit of the first class is 25, right? So if I'm zooming in on this, I'm looking at my first class. That smallest value is 25, and the upper class limit is 34, right? We're going from 25 to 34 on this table. And then the lower class limit of the second class is 35, right, and so forth. So the class width, as we talked about, is the difference between consecutive lower class limits, right? So if I take 35 minus 25, I get 10, right? So that is known as the class width. So notice I subtracted the two lower class limits for consecutive classes, right? You know, this data is continuous, your age. You don't go from 1 year to 2 year immediately, right? You continuously go towards the next one, right? So these would be continuous. So in other words, it's saying here, when you see the class 25 to 34, that actually represents 25 to 34.9999, so forth. So in other words, you're getting as close to 35 as you can without actually reaching 35, right? So you know, we could show that as the 25 to 34. We could show that as you know, x less than or equal to 25 less than 34, right, as an inequality. Or you know, you could show it in interval notation where you go 25 with a bracket, comma, 34. Well, actually, we'd write 35. Whoops. Yeah, actually, that would be 35 here too. Sorry. 35. And then 35 with a parenthesis, right? So if you were, you know, 34.7 years old, you would still be in this first class because you're not yet 35, right? That's what this is saying. All right. So the classes are not going to overlap, right? So you don't want it where someone could be in two different classes, right? That's not going to work out well. And then this says this table is open-ended because the last class has no upper class limit, right? So if we look at the last class, it just says 65 and older. It doesn't keep going, you know, with a class width of 10, right? So if we were to rewrite each of these classes in interval notation, right? This would be, the first one would be 25, comma, 35, where this would be a parenthesis and this would be a bracket, and then 35 to 44. Let's see, I don't have quite enough room to write. Let me just make some room here. We have 25 to 34, 35 to 44. and then we have 45 to 64, and then 65 plus 65 and older. So the interval notation, right, this would include values 25 to 35, and this would be a bracket, this would be a parenthesis, and then you would do 35 to 45, parenthesis, bracket, and then 45 to 65, right, so this would be parenthesis, bracket, and then 65 to infinity, right? I mean, no one can live to be infinity, but there's no real good cutoff, right? If you do 100 years, maybe there's someone alive that's 103, right, and so forth. So there's no real good cutoff here, so we just leave it as infinity, right, 65 and older. So this like means infinity. Right? So remember the bracket includes that value. Parenthesis excludes, doesn't include that value. Right? And we can never include infinity, so that's always going to be a parenthesis by that. So if you're age 45, right, you would be in this category, right, because you're included with this bracket here, but excluded here with the parenthesis. All right, so now we're ready to look at another example. So this is a data set for an unemployment rate for each state in January 2019. We want to construct a frequency and relative frequency distribution of the data. Right? So if we look through this, you want to find the max. Oops, still on the highlighter. We want to find the max, the min, and also the number of things we have, right? So I'll do n equals, and then maybe the number of classes that we want, right? So let's say we want to do 8 classes, right? If we count how many states there are, listed here, there's 52, and then we want to find the minimum number and the maximum number through this data set. So one thing you can do is if I bring over StatCrunch, if I click on this down arrow, I can click sort table ascending, and that will just put it in order from smallest to biggest, right? So I can easily see my minimum value is 2.4. And my max would be the last one, 8.4. Right. So using that sort function, and if you in Excel or in StatCrunch, that can be really helpful. Right. We'll also see how to find some basic descriptive statistics using StatCrunch later on, but that will also like spit out the max and min. But so then what we want to do now is calculate the class width, right? So and I'm doing this by hand, so that way, again, I'm going to do this the way that I demonstrated or suggested here. And this is like more methodical way to get for all of us to get the same histogram, same frequency distributions, right? So then if you remember the class width is equal to the ceiling of the max minus the min divided by the number of classes. So this is equal to the ceiling of 8.4 minus 2.4 all over 8, which this equals the ceiling of 6 over 8 which is the ceiling of, so 6 divided by 8, that's 3/4, so 0.75. So then we go up to the next integer, which is 1. Right, so the class width is 1 in this case. So then when you build this, right, we would have our classes here. We would go from 2.4, that's the minimum value, and then go up to 3.4 because we want a class width of 1. Right, we would exclude 3.4 from that class, right? Then the next one we would start at 3.4 and then go up to 4.4, so we do bracket and parenthesis, so forth, 4.4 to 5.4, 5.4 to 6.4. Right, and the idea is we want to have 8 classes, so I only have 4. Right. And then, so I only have 8 classes. We could add another one, 9.4 to 10.4. But my max is actually 8.4. So my maximum is going to appear in this class above it. So really we don't, need to write that. There's going to be nothing in there. Right. So then now we could make a column for tally. Oops. I accidentally erased that. Right, and then have frequency. And relative frequency. Right, so then we would just look through the data. So like this first number is 3.8. So I come down here and 3.8 is going to be in this class, right? And then come up here to 6.5. And then that value is going to be in here, right? And the next one's 4.9, so cross that off. 4.9 would exist in here, right? So go ahead and pause the video and do that for the whole data set, and then I'll go over the solution. Alright, so you can double check your work, but I filled in the tallies, the frequencies, and I went ahead and filled in the relative frequencies. Alright, so remember the total was 52. So I would, to get this relative frequency here, right, I would take 17 divided by 52, and that's approximately 0.33. So I rounded these to 2 decimal places, so you can do that all the way down. But that's our frequency and relative frequency distribution. Alright, so now objective 4, what we want to be able to do is to take that data and turn it into a frequency histogram, right? But before we do that, I forgot I was going to just show you how to do this in StatCrunch, right? So just as a simple reminder, right? So I'm looking at this data, the rate. So I would go to stat, tables, frequency, right, just like before. The variable that we're working with is rate, and I'm going to leave frequency and relative frequency checked, hit compute, and notice it's prompting you. It's saying, whoa, like lots of unique numerical variables for rate, want to turn on binning for this procedure, right, and click OK, and it automatically builds the bins, right? So you want to notice that the bins are different than what we made, right? Like our first class, ben and class are referred to as the same thing, right? So the first class or the first ben that we had was 2.4 to 3.4. So notice here it's listed as 2 to 3. So the class width happens to be the same, but the starting value, the value for the lowest class is different, right? And StatCrunch is going to pick those on its own, right? So it doesn't mean that it's wrong, but that's just another way to do it, right? So that doesn't match what we had, but same idea. And remember, they're both right? What we just did and what StatCrunch did, they're both right. There's not one that's more right than another. All right, so now we're ready to build the histogram of continuous data. So we're going to use that unemployment table, and I'm going to just use the frequency distribution that we made in example 3, right? So if you want to build it into a histogram, you would just build like we did before. So I'm going to pause the video and draw these, and then talk about what these look like. All right, so here are the frequency histogram or the relative frequency histogram for the unemployment data drawn out by hand. So just some things to talk about. Notice this symbol here. This is referred to as a line break, right? And that is just symbolizing that I chopped off the part from 0 to 2.4 essentially, right? So I didn't want to go from 0 to 1.4 to 1.4 to 2.4 and so forth. I just cut that off. If you wanted, it wasn't a big deal to list that here. It would just be some blank space, right? And especially if we start at like 10.4 to 11.4, you wouldn't want to have all that blank space. And then I just drew in the histograms like normal, just like for discrete data. So it looks identical. Right? Notice I have a title for each of my variables and a title for the graph. Right? So now I want to show you how you can build that on StatCrunch. Right? So if I go to graph and then I can go to histogram, and I want the rate variable to be a histogram, and here's where I can specify some things. So like for the frequency, I can pick to be frequency or relative frequency, so I'll just check frequency, and then these are referring to the bends. So I can say to start my bend at 2.4, and my bend width was 1. Right, notice it says optional in there, so if you left it blank, it would create, fill in those values itself, automatically. And then you can add titles here if you'd like. So for the x-axis, we could say the unemployment rates. For the y-axis was frequency, and the title for the graph, we had January 2019 unemployment rates by state. So I can go ahead and hit compute, and there's the histogram. Right? And of course, if I wanted relative frequency histogram, I could go to edit this, and I could just change the type to relative frequency, and it would make sense to add relative here, and the y-axis label, hit compute, and we get that. Right? Alright, so the next thing I want to do and in the notes, you'll see example 5. So I want to open up the unemployment data in StatCrunch, but we want to go to applets and then histogram with sliders. And what this is going to allow us to do is pick different values for the starting point and the bandwidth, and we want to think about, what happens. So if I go to applets, histogram with sliders, I want to pick the column rate, and I'll click compute. So here's a histogram, which has a starting point of 2 and 1. So that's what was chosen automatically. So what I can do is move these sliders and see how that impacts things, right? So for example, if I just move the starting point down to 0 and keep my bandwidth at 1, notice that the shape of the graph has changed, right, as we move this. So you can see how it alters different things. Right, so I'm going to leave that starting value at, so I think it was originally at 2. And then what happens when we change the bandwidth? So if I make the bandwidth smaller, notice how the graph is going to change. And if I make it larger, it also changes how the graph looks, right? So the idea is there's not just one correct histogram. Some are going to be more helpful than others, and some are just bad. But what you should notice is the shape changes, and we want to try to find a happy medium between having enough bends to know what's going on with the data, but we don't want too many bends, because then it's like too precise, right? Like if I take the bandwidth all the way down, right, this doesn't seem nearly as helpful as when the bandwidth was 1. Right, this is a much nicer shape to really see the distribution of data. And also, if I change the bandwidth all the way up, we only get 2 classes, so that's not really helpful either, right? It doesn't tell us much, right? So you just want to be aware that picking, appropriate starting points and bandwidths can change the shape of the graph, but also can be more helpful than others. Right? So that's what I want to show you for that one. So the next thing we want to do is draw a dot plot. So a dot plot is drawn by placing each observation horizontally in increasing order and placing a dot above the observation each time it's observed, right? So we want to draw a dot plot of siblings from the statistics class dataset, right? The siblings.csv. And one thing you'll notice when I worked with this data set and I changed the order of the rate, notice it left spaces and moved the siblings numbers around as well, right? So in other words, it keeps the rows together. So I'm gonna sort this ascending for siblings, and that kind of puts the siblings numbers in order, but groups all the siblings back together. Right, so that's just one way you can do that. So and typically, when you're working with StatCrunch like this, we wouldn't want to list these variables in the same sheet, because these variables don't go together, right? So typically one row is like one person, and each of the variables go together. But I did this just for ease to put siblings here and state and rate, so these things aren't related at all, and that's why I left a blank column in between, right? But typically you wouldn't do that. I'm just doing that for ease for this video. Right? So we want to draw a dot plot for the siblings in the stats class. So we just need to draw like a first quadrant. We can give this a title. We can call it the number of siblings of honors statistics students. So down here we'll have the number of siblings. So 0, 1, 2, 3, 4, 5, 6, 7, and so forth. And then we don't put anything here, right? And then you're going to draw circles to represent one data point, one observation, right? So in other words, if we go way back up when we were talking about the siblings, when you see this number 5 here, instead of drawing a tally mark like in a table, you're going to draw a circle, a dot, up above the number 5. And then every time you find a number 5, you're going to draw one right above it, right? So you would do that for each of these. So for 0, there was only 1, so you would just draw one circle. For 1, there were 4, so you'd have 1, 2, 3, 4. Oops. And then for 2, there were 8. For 3, there were 3. And when you're drawing these, you want to try to make the circles the same size, the spacing between the circles be the same, and so forth. The idea is the taller the bar should mean more observations in that category, right? So you want to try to do this correctly. It's kind of hard to do by hand, right? But that's the idea. If you wanted to do this in StatCrunch, you're going to go to Graph, and this time you're going to pick the dot plot option, and the variable we want siblings this time. So I'm going to hit, I'm not going to add an X and Y axis and title this time, but you could do that if you wanted. I'm going to hit compute, and then so there is a dot plot, right? Computer generated. So the spacing in between the dots and the size of the dots, those are going to be consistently the same, right? That's the nice thing about using a computer. Right. So then the last objective of this section is looking at the shape of a distribution, right? So we have here 4 distribution shapes and like a definition, like description. So a uniform description, or excuse me, a uniform distribution is the frequency of each value of the variable is evenly spread out across the values of the variable, right? A bell-shaped distribution is the highest frequency occurs in the middle and frequencies tail off to the left and right of the middle. Skewed right is the tail to the right of the peak is longer than the tail to the left of the peak. And then skewed left is the tail to the left of the peak is longer than the tail to the right of the peak, right? So if we look at the next page, these are just some pictures of histograms of that, right? So this was uniform, right? So it kind of looks like this box shape, right, if you will. So notice it's like flat, like everything's about the same, right? An example of where that might come up, a uniform distribution, would be, if you like roll a die, right? We would expect like an equal probability for rolling a 1, 2, 3, 4, 5, or 6, not one more than the other, so that's going to be uniform. And then the next one is bell-shaped. So notice the bell-shaped curve looks, something like this, which looks like the side of a bell, right, if you will. Like if you look up a picture of like the Liberty Bell, it kind of looks like the side of that, right? So if I draw kind of like the overall shape here, you'll see that looks like a bell. And notice also both of these, the uniform and the bell-shaped, have the symmetrical word attached to it, right? So symmetrical meaning it's like a mirror image, right? There's a line of symmetry. Oops, it's not wanting to let me draw. Right, so like if I draw a line like here, there's like a line of symmetry, right, somewhere in the middle. right? So the next one is skewed right. So notice this one looks something like this, where what it's referring to is it's kind of like a bell shape, but this hill was kind of pushed over towards the left, right? So the distance from to this tail, and then from this to this tail, is this one's longer, right? Where this one's shorter. So right skew is when that hill is like shifted towards the left, right? And then skewed left is when the hill, this hill is like shifted over to the right, right? So it's kind of like the opposite in that sense. And we'll look at some other, when we talk about like mean, median, mode and things, we'll talk about some other, rationale, maybe why we use skewed left or skewed right. But those are some examples. So if you have a symmetrical, bell-shaped data set, an example of that might be SAT, ACT scores. So those are what we call like normally distributed. Skewed right, classic example for that would be like income. Right, you're going to expect more people to have fewer income and less people to have like a large income, right? So like over here it's like, the rich people, right? There's very few, so there's little bars, where the bulk of your people over here are more, less off, right? So that would be one example. And then skewed left. So I was trying to think of a good example for skewed left, and I think what I came up with, what I think would be skewed left distribution, was if you looked at like marathon race times, right? So my line of thinking is there's going to be few people with those really short race times, and maybe there's like a big bulk of people like that don't run nearly as fast as the winners, right? So that's one possibility, right? And then notice there's a caution here that we do not describe qualitative data as skewed left, skewed right, or uniform, right? So we use these terms for quantitative data. And then example 7, the last example here, is to identify the shape of the distribution for the unemployment data, which was from example 3, right? So if I go here, so we want to go to graph, histogram, we want the rate, hit compute. So here's just a quick picture of the histogram. So this appears to be skewed right, right? So notice the overall shape. There's like a big mound, and then there's like this long tail towards the right, right? So the general shape of this histogram, it looks something like this. So this is skewed right, right? And another term for skewed right, we say positively skewed. And another way to say skewed left is negatively skewed. Oops. So you might come across that from time to time. All right, so that's all I have for this section. Let me know if you have questions. Thanks.